Okay. So what we can do with that is then we can test the ether diverter. So this device has been operational only since about 2017 with this superconducting magnet. So quite recently, we've got this operating with the superconducting magnet. For a few years prior to that, it operated with copper coils, which didn't make us a higher magnetic field. And so what that means is that we can do these high fluxes and high fluence and investigate what happens to the material within a reasonable time frame. So ether is going to operate for shots that run for about 5 minutes at a time, and they're going to then wait and they do a shot every couple of hours. So in a day they do perhaps 10 or 12 or 15 shots, and so over a year they get to a cumulative fluence, so number of particles of about 10 to the 30 particles per square meter arriving at these strike points. And in the same time, if we just do that continuously in one shot, we can get there in 20 or 30 hours. And so that means that we could really, do a preview of what's going to happen to the material ahead of time. So that's what we did. We took a little tiny piece of the diverter. So this is 7 of these blocks that I showed you earlier, mounted onto a cooling tube, and then it's mounted onto our mounting system. There's water flowing through these pipes here to cool this whole thing, and then the plasma is going to hit just one of these blocks at a time. And so what we did was we wanted to find out, well, how do these monoblocks perform when we sort of recreate these conditions on a long time scale? So we try and recreate 1 year's worth of operation. And we exposed 4 different ones of these blocks on this chain to different conditions relevant for different stages of the ether operation. So ether is going to start out at sort of a low power when they get started, just to kind of make sure that everything's working. And over time, they're going to build up to the full fusion power operation where they make lots of fusion energy. So we wanted to go step by step, what happens at each of these stages for the material. And I don't want to get into all the details, but we were interested in a bunch of different things. So we wanted to find out what happens to the hydrogen, where does it go inside the material? There's also going to be helium present from the fusion reaction. So one of the products from the fusion reaction is helium. And that's also going to come and hit the wall. And a lot of strange things happen when helium interacts with tungsten, actually. So you get all sorts of nanostructures which form. We want to investigate that. And actually, just because there's also a lot of heat and the metal gets very hot, that also has a lot of effect on the properties of the material. So the actual microstructure of the material starts changing. So without digging into all the details, metals are basically made of a bunch of tiny little crystals that are all joined together in a bunch of, when you heat the metal up to a very high temperature, then the crystals actually start to deform and change and move around. And so that also changes the properties. So we investigated that. So this is just a picture on the right, shows you the plasma beam in action. So the plasma source is on the right, and you can see it hitting just one of these blocks, and you have this big glowing area where the plasma beam is hitting the block, and a little bit of the plasma is also going past the block, so the beam is a little bit wider, so you can see a part of the plasma coming past. And the good news is we were able to do this. So we did 1 year of ether operation, and we did it in about 20 hours of continuous operation. And you can see here a picture on the bottom left. These red circles represent where each of these plasma spots was. So we have 6 different plasma spots. What we actually did was we flipped the target over, and we did 3 on the front and 3 on the back, and we did a spacing in between just to try and isolate each of the different conditions from each other. As you can see, there's a little bit of overlap onto the blocks on either side of the one that we were interested in. And all these different spots then show some different measurements that we did in different positions. And I'm not going to dig into any of the details of what we did. The bottom line is that we found some interesting stuff. So for example, here's some of this weird nanostructures that grow on the surface of the tungsten. So these are tiny little tendrils that grew up in certain places, which are called fuzz. And these grew when you have the helium plasma. And we chopped these blocks in half afterwards and had a look at them afterwards. And we found that in this top region here, where it was hottest, we see this change in the microstructure of the material, and we investigated that. So we do see changes that happen because of the plasma exposure, but the good news is that nothing that was a showstopper. So we believe that these targets are going to work just fine for ether operation. However, the story does not end there, because when you go from ether to a reactor, so this demo that I mentioned earlier, a lot of things get even harder for materials. And two things that change are that we want to make much more fusion power to be able to actually generate electricity and put that on the grid. And we're going to operate, instead of operating for 5 minutes at a time or 15 minutes at a time, we want to operate for hours and hours at a time or days at a time, because we want to always be continuously making electricity, and you don't want to be always turning your machine on and off. So you want this thing to run in a near continuous way. And so when you combine the fact that we have more fusion power and we're operating for a much larger fraction of the year, so that's called the duty cycle. So the duty cycle for a power plant would typically be 60 or 70%. That's what we'd be aiming for. So 2/3 of the time the plant is operating. If you compare that to ITER, the duty cycle is only about 2% of the year. For something like current day devices, these normally operate for a few seconds at a time, and then they do, again, 20 or 30 shots a day. So the duty cycle is very short, maybe 0.1% of the year you're actually on. And the second thing is you have a lot more fusion power going on, and every fusion reaction creates a neutron. And so every neutron that hits a material can do damage to the material. And so the amount of damage is called displacements per atom. And basically, in current day devices, we have almost no displacements per atom. So we have very few fusion reactions happening. So 1/1000th of a displacement per atom is typical for what material would experience in jet. In ITER, over the lifetime of the divertor, we think it's going to get about 1 displacement per atom. So we've gone a huge step up in terms of neutrons. And then if we go to this demonstration reactor, we go another factor of 100 up in displacements per atom. So the neutron damage in a reactor is going to be much, much larger than it will be in ITER. And so that's very tough for the materials as well. So it's much larger fluences of particles that are coming to the wall. Heat loads may even be a bit higher because we have more fusion power going on. And also the amount of neutrons is way bigger. So this gives extra challenges for tungsten. So because the fluence is much larger, the amount of erosion that happens is much greater. And so over time, your wall can be eroded. And so we have to worry about whether or not we have a thick enough wall that it will survive for long enough to be economically achievable. We're going to turn this machine on and off all the time over many cycles. And also you can have transient events that happen in the plasma that give extra little thermal cycles that happen on top of the surface of these blocks. And that can lead to cracking that happens. If you turn something on and off, imagine if you stretch a rubber band many times, over time that rubber band will snap because it gets weaker. And the same thing can happen with your tungsten, that if you heat it and contract it and heat it and contract it many times, then also it will crack. And if you have some big transient events, which can happen in these reactors, then accidentally you could melt the surface of your tungsten. And that's a bigger risk in a reactor than it is in ITER. And as I mentioned, these neutrons will just, over time, they degrade the properties of the tungsten. So they come in and they hit the material, the atoms, and some of those atoms are transmuted into other elements. And also they will just knock atoms out of the lattice that they're sitting in, this lattice of atoms. And that also causes damage over time. And so if you look at this picture, this is a sort of cross section of what our wall looks like. So we've got these monoblocks made of tungsten with our coolant pipe around it, with some water flowing through it. And we have a different idea of how we could design a new wall. We want to use a liquid metal on the surface of the wall, which has a lot of advantages. So what we would do is we sort of make our wall a bit thinner, and we add a layer of liquid metal, which is sitting inside a sponge. And this sponge is made of some sort of mesh or felt or something like this that has that holds it in just like a sponge holds water in. So by surface tension forces, it holds the liquid metal in place. And then you have a reservoir of liquid metal which you can supply to this surface. And so the advantages of that are several. So now you don't need to worry about erosion anymore. So you can always have new liquid which flows in to replace any liquid which is eroded. And of course, a liquid cannot crack, and the liquid is already molten, so you don't need to worry about it melting because it is molten. And as I'll mention in a second, it can also protect itself by a process called vapor shielding. And also a good thing about liquids is liquids don't really have a lattice structure. So if the neutron comes along and it knocks an atom around, that isn't a problem. A liquid is a fluid, so these atoms are all mixed up and jumbled up together. So its properties are not strongly affected by the neutrons being there. And so it's much more resilient against the neutron damage that you would have. So that's also something that we're investigating now at DIFR with Magnum PSI. So I'm just going to tell a little bit about an experiment that we did to investigate metal vapor shielding in Magnum PSI. So if you have your liquid in this sponge and you heat it with the plasma, some of the liquid, when it gets hot enough, will evaporate, and that actually forms a gas cloud, which is in between your plasma and the wall. And so actually the interactions of this gas cloud with the plasma cool the plasma down and take some of that heat away so that it doesn't arrive at the cooling water. So without wishing to include too many equations, I included two here just to kind of make this clear. You've got a heat load from the plasma, and in a solid, all of that heat has to be taken away by conduction through the water to the water cooling. In a liquid metal, you have the same heat that comes from the plasma, and you have to take some of that heat away by conduction, but you also have heat loss by the evaporative particles leaving, and that takes some heat away. Radiation from this gas cloud, so that some of that energy is radiated away to other areas. And you also have a process where actually you will neutralize some of the plasma, and then that mass of the plasma is lost, and it also will be transported elsewhere. And so then you're basically lowering and limiting the amount of heat that comes to the surface. And that means that the wall cannot overheat and the coolant cannot overheat. So it's a self-protection mechanism which you get from the liquid. And so if you put all of that together and you make a prediction, as you increase the power that comes from the plasma, so that's what's on the x-axis, when this vapor cloud isn't present, you can imagine that just as you increase the power, the surface temperature is just going to go up linearly. So at some point, if you keep on doing this and you imagine that you just have a solid, at some point you reach a limit where the tungsten will melt. So you keep on imagining you follow this line up forever, then you get to the melting point of the tungsten. However, if you've got this lithium, which we're using as the liquid metal, as the surface, on the surface, then eventually these other processes become dominant and it leads to a saturation in the surface temperature. So basically the surface temperature can't go up anymore because even as the surface temperature goes up, the evaporation goes up very strongly, and eventually there's so much liquid which is evaporating into the plasma that you have a locking effect. So the surface temperature cannot increase anymore because then the evaporation would increase, and so you have a sort of self-stabilizing mechanism where it just locks at this temperature. So that's the prediction that you would have from this theory of what you would expect to have with the vapor shielding. So to investigate that, we did an experiment in Magnum PSI, and now you can see
just as a short interjection. Sure. I'd say you have about 2 minutes left with my overtime as well. And there was one question in chat from Mitchell, which is, wouldn't you still have to replace...
this is like more or less my last slide, Ralph. I've got one more slide after. Okay.
And then one question for afterwards, let's say.
I'll try and be quick. So in very brief, we have a cross section now. You can see the plasma source over here, and over here we have the target and the plasma beam coming along. So this just shows you what it looks like inside Magnum. And we put the liquid metal inside a special 3D printed tungsten sample that we made. And here you have a reservoir of lithium, and it's shaped in such a way that it draws the liquid metal up to the surface. And here you have a very fine texture that acts like a sponge to hold the liquid metal in place. You can see a picture of it here. So in very short, what we did was we did the experiment, and this is now time. So over time, what you would expect to have for a solid material is that you heat it up, and at some point we reach an equilibrium where all the heat is, where the conduction of the heat is equaled by the to the plasma coming in. We reach an equilibrium. So this is a sort of curve that you expect as you heat something up. It heats up, and then it gradually just equilibrates to a certain temperature. When we do it with the solid lines now, these are with the lithium present, then you see that you have this increase that's going up, and then suddenly it locks at a certain temperature. And what's nice to see is that this lock-in temperature is what we predicted from the theory. So it's a nice example just to show that this vapor shielding effect really works to help protect the surface. So that's the last thing. These are my conclusions. So just the takeaway messages are that, you know, one of the biggest challenges for fusion is controlling this heat and making sure that we avoid damaging the wall. Very nicely here in the Netherlands, we have one of the best devices in the world for investigating this, which is Magnum PSI. So it's very nice that, you know, the Netherlands is a small country, but we have a really top-notch device to investigate this here. And also to note that when you go from even ITER up to these demo reactors, then it makes this problem harder. But we have very exciting new solutions which can help to solve this problem, like liquid metal walls. Okay, so then let me have a look at the chat and see what was the question. The question was, I see two questions. Wouldn't you still have to replace the mesh that keeps the liquid metal in place? So that's a really good question. So, of course, the mesh, this sponge, whatever it's made from, this is solid, right? And it's going to be made out of tungsten most likely. And so that still has all the problems that neutrons will damage it over time. However, the difference is that it doesn't have to be as strong as when it's a solid block of tungsten. So because you have this liquid in between it, it can be quite weak. It's not a structural material, and so even if it's embrittled by the neutron loading, that tends to be what happens from neutrons, is that they make the materials more brittle. It doesn't have to have, it doesn't undergo such strong stresses, and so it will be better able to handle the neutron loads. Then the question is, have you patented the liquid wall? I wish. It's not. I have to admit, this is not my own idea. There's many people in the community that have thought about this, and to be honest, I would say that fusion generally is not at the stage where patenting things is what we're doing. We're really doing research, and we all want to be open and communicate and publish things in journals. And so, we're not at the point where we're trying to commercialize this. So this is open information in the literature. So it's not something that's really patentable. However, if we came up with a specific solution that was particularly good, I guess we could patent that. And that's another excellent question. Why choose lithium for cooling and not another element? So there are many metals that you could choose. And one consideration is you want to have a liquid metal, of course, which is relatively available and which has a relatively low melting point. So that already gets you down to only a handful of elements that have those properties. So you could perhaps use mercury, lithium, tin, bismuth, or gallium. Those are the main low melting point metals that have, let's say, a melting point below 300 degrees C or so. Of those, lithium is very good because it has it's element number 3 in the periodic table. So that means that because it's low Z, it doesn't pollute very much the core of the plasma. So basically, the lighter the element is, the less problems it makes for the core of the reactor, because you can tolerate more impurities in the center of the reactor than if you have a heavier element. So that's why lithium is a good choice. There's actually two main leading options. One is lithium and the other is tin, but the designs are slightly different for each of those. So without going into details, those are the main choices, and it's also to do with how corrosive the materials are. So, for example, gallium would be a good option, but it's quite a corrosive metal, so it's hard to make it compatible with all the other elements in the reactor. Are there any other questions?
No, I think that's all of it.
I think there was one a bit earlier during the presentation by Van Soest. Stopping the B for the plasma current will decrease reverse current. Is there still a question left there? If not, then we can continue. If there is a question, you can also put it in the chat, and then we will respond by chat, because we are running a little bit over time. So I would suggest that we now take a 10-minute break instead of a 15-minute break.
I think if I understand the question from Van Soest, I'm sorry, I don't know what your first name is. I think if I understand what their question is, they're asking, so you want to, if you drive this this current in the tokamak to make the poloidal magnetic field, at some point you have to stop driving it, because you sweep the voltage from a very negative voltage to a very positive voltage, or vice versa. So that's basically, you have to drive a current by stepping from one voltage to another voltage through your transformer action. And so what happens is then that you then have to sort of recharge that. And so all inductively driven devices are pulsed devices that can run for a certain number of seconds before you run from one end to the other. And so that's why people would like, one reason why people would like to have non-inductive current drive, because then you could run in steady state. and that would be a big advantage. So I think what you're asking is, yeah, if you would reverse the current, then you would reverse the magnetic field, and you could then go back the other way. And the difficulty with that is that normally everything is designed and shaped so that you have the currents going in one particular direction. So for example, you make fish scales on the tiles to protect the leading edges of tiles because the plasma is flowing in one particular direction. And if you reverse the current, then then everything also goes in the opposite direction, and the drifts are in a different direction from what you expect. So that makes things a bit more complicated.
Yeah, but
I hope that helps to explain what you were asking. I hope that was what you were.
Yeah, the problem is when you stop the current, the magnetic field decreases. So you turn on magnetic field turns on the direction.
Yes. So basically what we do is we make sure that we start this current, and then we put some heat in after a few seconds in the plasma, and then we kind of end the plasma shot before we run out of current loop. So you kind of end the discharge before you run out of magnetic field, if that makes sense. Okay. So you ramp up and then you ramp down again. So you go up from 0 to some mega amperes of current, and you ramp down again to 0. That's how you design it.
Okay.
And so the plasma starts off as a very thin, small region, and it gets bigger, and then it shrinks down again.
Okay, it's not that easy.
Yeah.
Okay, thank you.
It's not so easy actually. This is a whole subtopic of fusion physics, is ramp up and ramp down and start up and ending plasmas. So that's actually a whole subtopic of how best to do that in the right order, and exactly what is the best route to do this.
All right. Thank you.
Okay.
Well, then it's perfect 11:30, and I suggest we have a break until 11:40. So tot 20 voor 12. Dan zullen we weer hervatten.
All right. Ik denk dat we weer langzaam kunnen gaan opstarten. The next talk will be by Jonathan Citron, who will be talking about the uses of artificial intelligence in fusion. So that will be a very interesting talk for sure. And I think I'll give the floor to Jonathan now.
Thanks, Ralph. And nice to be here. And I'm happy for the opportunity to give this talk to you all. So I am Jonathan Citron. I lead a group at Differ on integrated modeling and transport. That can be translated as essentially tokamak simulation and plasma turbulence. And these are also themes which will be covered by the applications of AI in fusion in this talk. Right, so I'm happy about the background being provided before by both Ralph and Thomas. So this is kind of continue based on some of the background you've already heard, and to motivate why we need these applications of AI in fusion. It is wholly related to the fact that we are really moving towards the next stage in fusion science and engineering, where the next stage of experiments will be at a scale much larger than ever before. And so this is most clearly seen in the ITER project being developed now in the south of France, the International ITER project, which is projected to produce 500 megawatts of fusion power from the plasma. And currently under construction. You can see here some very nice recent pictures from a few months ago about how massive vacuum vessel sections are now being delivered on site with huge magnets being welded to them. The tokamak pit is ready. Initial components are being lowered in there. So this is in full swing. And at the same time, we have advances in high field superconducting magnets, which have parallel exciting developments, perhaps for a smaller and faster branch of tokamak development. I think most represented here by the MIT spin-off Commonwealth Fusion Systems, who also plan to have a burning plasma for the first time, with experiments beginning in 2025. So what these new generations of experiments have in common is that they really demand, together with their leap in scale, also a leap in our simulation capability. And this is important because present day experiments, smaller, more nimble, smaller teams You can afford to make mistakes. You can afford to do iterations of the experiment in the control room. You can spend a lot of time tuning things by hand. However, the next generation of experiments, each one will need to be pre-simulated. To reduce costs and risks, simulation will be vital to prepare each experiment before they're done. Also, to reduce the number of experiments needed by performing optimization of experiments based on accurate models. We'd like to use simulation for control. We'd like to be able to understand ahead of time what the plasma is going to do when we turn the knobs, a little bit akin to how you can design the trajectory of a car by seeing how the road turns, and you know what kind of action you're going to do when you hit the gas pedal or turn the wheel. So we'd like to be able to drive a tokamak and plan these both the feed forwards and the feedback control of the tokamak plasma, also based on modeling. And we'd like to use models even to design future reactors if the models are accurate enough. So we need a leap in simulation capabilities, and AI can play a very important role here. So I'm now going to take a little bit of a break from tokamak science and introduce you guys to machine learning and artificial intelligence, because these techniques, they play a growing role now in as it is in the rest of society in fusion science, due to its role in accelerating simulations. And even when we don't have available models, and we can go deep into this afterwards on what we can and what we cannot simulate. But even where we don't have models, AI can make predictions based on previous data. It's called data-driven modeling. So what is machine learning? So machine learning, it's a large group of mathematical techniques and algorithms. So what they have in common is that these are algorithms that learn from examples. You have to show it many examples of what you'd like it to predict. And then these they learn how to generalize to predict new cases that it hasn't yet seen. Okay, so to put it a bit mathematically, you can show these algorithms a function f of x can be some vector, and you can show it many examples of x, different sets of x can go in there. It sees many examples, and then it can actually learn what the function is f when you give it a new value x it hasn't seen before. It can accurately predict what it should be. And these techniques are used both for, I think, the more famous examples of machine learning, pattern recognition, so discrete. So I can show you examples soon, but if you have a picture, you can imagine X as being a big vector of pixels. Is it a cat or is it a dog? Okay, so pattern recognition, but also, as you'd maybe be more used to it from just continuous functions, you can use this to fit, it's a regression, continuous functions as well. Like simulation model input and output. And this is where we use it actually in my group. Okay, so these can be measured data and labels or simulation model input and output. And let's take a look at a few examples then of how to think about the things that machine learning techniques can learn. So if we think of our function f of x, famous example is handwriting recognition here on the bottom left. Oops, sorry. Yep. So x is a matrix of pixels. It can be very simple, even without color, black or white. And then each collection of pixels with zeros, black or one white, people beforehand have labeled a whole bunch of these as numbers, in case they have labels. And then the algorithm is just showed a bunch of these labeled matrices, and then eventually learns to correctly identify which numbers they correspond to. So and similar ideas can be taken in more modern cutting edge pattern recognition, such as how to caption an image, a person on a beach flying a kite. Okay, so each time you click on a kafta when you try to get into a website to say, please identify where all the trucks are, you're actually helping the algorithms to caption images. So that's often the bottleneck, that people have to label these things beforehand so the algorithms can learn from. But in terms of, let's say, science, so you can think of drug discovery, molecular composition, and the function of that for its effectiveness. Material science, you have some composition of materials. What's a given property that you'd like to predict? And then for our cases in fusion science, you can think of real-time controls. You have some recent measurements from the past. You have a time history of measurements. What's going to happen next? Okay, so you can train on many experiments and begin to predict what's going to happen. Or in what I will discuss in more detail, talking about turbulence, you have a bunch of local plasma parameters. So what is going to be the turbulent level, the flows of heat and particles? So there are many techniques in machine learning. So among the most famous is neural networks, which has many, many various topologies and forms and types. And what they do essentially is they provide a very powerful framework for fitting. Okay, so here you can see a typical topology for image recognition. These are called convolutional neural networks. What they do is they take this initial input image. So these are now pixels with different values for, red, green, blue for colors. And so you have all kinds of mathematical operations that essentially do convolutions of these and averaging. So it's called convolutional, and then reduce its dimensions. And then they put it through all of these nonlinear functions with linear superposition between them. These are called fully connected layers. And in the end, you have some kind of, that if you have some vector, and if most of the vector is closest to 1 somewhere, then you sort of clip everything to 1, the rest 0, and then you can see the probability. Is it a bird, a sunset, a dog, a cat, or so on. So all of this, you have to imagine that this is just a chain of mathematical operations. Many of them are linear, some of them are nonlinear. On the way, you have sometimes functions like tan h or sigmoids or things like that. But essentially, there are many, many free parameters in here. So all of the linear superpositions, what are the weights? How do you multiply everything? So in the end, you have this very long, complicated mapping of pixel value to what is the probability of what kind of label it is. And so the whole point of the algorithm of machine learning is how to change all of these free weights such that you maximize the correctness of identifying your input to your output where they're known because you've labeled them beforehand. This is called supervised learning. And you crank it through, and essentially what this is a global optimization problem for all of these free weights in these networks. And it is a tour de force of calculus. This is the mother of all chain rules. So, a very interesting literature about it. And actually it's not such black magic in the end. What has led to the breakthrough in the past 10 years is very smart, powerful optimization algorithms and software frameworks and more powerful computers. So this was the crash course in machine learning techniques. So then why is it important for us in Fusion? So I think as Ralph has mentioned, one of the major challenges we have in Fusion is the existence of turbulence, which effectively limits the attainable, or is one of the limiting factors of our plasma temperatures and densities. So what we'd like to do, of course, is to be able to optimize. You heat a plasma. So here you can see in the middle of the plasma, you have, it's very hot, 100 million degrees. You wanted to maximize the temperature up to a certain degree to get your most fusion power. But these large gradients are making turbulent flows, and they get an outflow of particles and heat or so on. So it's been huge breakthroughs in the last 20 years of plasma turbulence theory and computation that we can actually calculate this with direct numerical simulation with supercomputers. But this is much too slow for very convenient simulation. If you want to do optimization, you need to do these calculations many, many times. You can't spend millions of CPU hours each time if you want to try to optimize your profile. So the question is, can we develop both fast and accurate turbulence models? So here, neural networks play a very important role that they can help circumvent this conflicting constraint of fast and accurate. And I'll show how we do it in our group by bridging 12 orders of magnitude in calculation speed. So the anchor point, kind of the golden standard, is, as we just showed, is this expensive nonlinear turbulence modeling. So this takes around 100 million CPU hours on massive supercomputers per calculation. By calculation, I mean to simulate a radial profile of tokamak temperature and density. A key point in which for this one needs tokamak turbulence theory knowledge is how to develop a reduced order physics model. You can't go directly to the neural networks because this is too expensive to make the training sets you need to actually learn from. You need something in the middle. And what's in the middle is a reduced order physics model that correctly captures the nonlinear physics, but it does so much faster. And this is through physics approximations and essentially. So these exist. We actually co-develop one of the main models of this type called Qualikis that differ. And this gets you about 1 million times faster, and you can begin within a few days each time to simulate these profiles of temperature. And then what the neural networks do is they actually can learn this reduced order physics model. So then you get the same thing back that's then even real-time capable, as shown in this example of a in a control-oriented simulator doing an ITER prediction. So the basic idea here is then, okay, so we have these, we have a validated reduced order model, sorry, down here, which is tuned to nonlinear simulations, validated against experiments. This is an entire subfield in itself. But then the idea is we actually use this model and we use actually supercomputers to then generate millions and millions of runs, of cases of them in parameter space relevant for present and future experiments. Then we use the neural networks to learn that database, to learn the model input-output mapping. And then we actually use the trained neural network as a drop-in replacement for this reduced order model in tokamak simulation. And then we get something that in the end is 1 trillion times faster than these anchoring nonlinear simulations. So this is really combined domain knowledge of both machine learning and tokamak physics to achieve this. And actually, I showed before all these fancy convolutional neural networks, image recognition. In terms of the machine learning, you don't actually need something very fancy to achieve this kind of fit. It's just pretty standard feed-forward neural networks where you have an input layer, which are local parameters like temperature gradients, density gradients, magnetic field geometry, temperature ratios between the ions and electrons, all kinds of stuff like that all influence the turbulence. And then your output layer is turbulent flows of particles, heat, momentum. And in the middle, you just have these chained nonlinear functions like tanh, which are general enough such that you can actually fit any input to output mapping. And then based on the database, it learns this database. It's called a training set by optimizing all of these weights doing the linear superposition of these nonlinear nodes. That's how neural networks work. Now, why is this so important to be fast? So I hinted before, but I just want to accentuate it again because to do this is very technical, but once you have it, you can also make physics breakthroughs because the system is a complex system, which is also characterized by self-organization. Okay, because the turbulence is sets diffusion and convection transport coefficients in transport equations. So this is conservation equations. You have partial differential equations for density, temperature, momentum, or so on, where the turbulence sets the flows, convection, diffusion, and then this sets the temperatures and the densities and the rotation in the plasma. But then the exact values of these temperatures and densities and their gradients feeds on the turbulence, which then again impacts the diffusion and convection. So it's a very nonlinear system. And the key to sometimes achieving optimized confinement regimes, where you can get very high temperatures, is as taking advantage of all kinds of bifurcations or positive feedback loops in this nonlinear interaction. And you can only, it's very slow to explore them in experiments, but with modeling, we can maybe find these optimized confinement regimes and then test it in experiments. So this has not been possible until now because we have not had fast enough models, but AI can really help to do this. And just to show an example that we actually have such a model and applied and validated in simulation, some recent papers from our group. This is looking at the jet tokamak temperatures and densities. This is with a neural network model inside a tokamak simulator in agreement with experiments. So this is actually being used now in research to begin to help us optimize these these experiments. So I'd like to conclude then with one other branch of how AI can help in Fusion, and this is more on the data-driven side, on pattern recognition. So this is not actually what I do myself, but I'd like to just report on it because it's very interesting and there's a whole other branch of how AI can be used in Fusion. So this is to be done when you don't have sufficient models to predict things accurately, but you want to learn from data. All the information of all the experiments done in the past can be fed into machine learning algorithms to help us predict and how to optimize future experiments. So one very important class of event to learn more about in tokamaks is called disruptions. Now, a disruption is when you have some very big instability or something goes very wrong in your experiment, and you have a sudden catastrophic loss of plasma confinement. Now, this is not dangerous. It's not dangerous for people, but it can damage the machine. Okay, so this wants to be avoided. It's not so bad in present-day machines, but if you're in a reactor, you really want to avoid the possibility of these disruptions, both passively and actively. And so the prediction of when you're in a regime that there's a chance that disruption can occur is really key, because you can mitigate it by the right control schemes. You can make soft landings. So it's only really dangerous if you have no idea that they're coming and then suddenly they hit you. And so there are many techniques already now to help with this, but the more layers we have, defense in depth is really important for them to have the high availability and machine safety. So this is a important subfield for AI. It's very suitable for what's called time series prediction. Okay, because we want to see from all the measurements done up to now in the experiment, what are the chances that a disruption is going to occur in the next second? And this is the kind of question that the algorithm wants to answer. And so there is a class of neural network called recurrent neural networks that encode information from time history to predict future events. And I'll just show just a little bit of the structure here. So the idea is that you have a sequence of inputs, like a time series. This could be some kind of measurement which is time-based, and these are all these X's in the back. And at each node in this neural network is then predicting some, the possibility of some state. For example, will this plasma disrupt? Yes or no? This kind of thing. But all of these states are actually connected from the past. And so you also have, so it's also learning, each node is also including information from all the nodes that were before it in the time series. Now, a standard RNNs, they've historically had problems with very long-term memory dominating the system, but there's a new class of these recurrent neural networks called long short-term memory that has some internal structure that allows you to tune a little bit the forgetfulness of each node. So you can kind of choose what is the horizon that you think is relevant for your problem, and then use that to try to learn to do your predictions based on time history with a given horizon. So this has been used, this technique has been used in Fusion. There's a Nature paper from a couple of years ago where there's been a very detailed input to these LSTMs, where you have from a tokamak all kinds of time signals, like 0D time signals of all kinds of diagnostics and measurements, even real-time measurements of things like temperature and density. They go into those convolutional neural networks that we saw before. And then the outputs of those are also being optimized. And then the whole thing is fed into the time history in order to predict, is this thing going to disrupt or not in the next, and it's not only important that it says, yes, it will disrupt. It's how much before the disruption is it going to predict, guys, this thing is going to disrupt, do something. And so this kind of technique has actually now have the record performance for disruption prediction at the JET tokamak, where you see that it's getting, for example, 97% accuracy of disruption, even something like 50 or 100 milliseconds before the disruption happens, which is more than enough time for the control system to do something about it. So that example, I think I'd like to conclude, and hopefully we'll have quite a few minutes for discussion. So what I presented here was that to have fast and accurate prediction of fusion plasmas, especially for the next generation of experiments, is really key to both design the experiments, optimize them, and for control. And the machine learning techniques provides a pathway to both accelerate simulations by just learning existing models and making what's called fast surrogate models based on them, to open up a whole new field, basically, of model-based optimization and control. And they can also provide predictive power based on data by learning from past experiments. And I showed a couple of examples. In general, this is quite a new field. We're just starting, and there's plenty of scope for machine learning to accelerate progress in fusion science. And if there's any, beyond these questions, if you have any further questions, my email is here. And we also have some information on the website regarding the Turbulence surrogate model project, which I mentioned. Thank you.
Thank you for your presentation, Jonathan. I see that there are some questions in here. So I suggest we go through the questions and then see where we are.
Yeah, so I see a couple of questions, so I'll just answer them here. So how do you know that your reduced model is appropriate for feeding into the neural network? So that is an excellent question. And there's a whole separate field of development and validation of these reduced models, because typically they're fast enough that you can use them for tokamak simulation, but maybe not at the speed that you need for the extensive optimization and control applications, but you can still use them in tokamak simulators to see whether they are accurate or not quite extensively. And this is done, I mean, people do this as careers, development and validation of reduced models. So once you have a certain degree of validation that you are confident with, then you can say something, whether it's appropriate or not, to then develop a surrogate model of neural networks to do the same thing, but much quicker. If there's no comment on that, then I'll move to the second question. Are the hidden layers based on physics law or correlations? Yes, that's another excellent question. So they don't have to be, but it helps if they are. There's a whole subfield called physics-informed neural networks, or physics-informed machine learning, where you can try to incorporate anything that you know about the physics in these models that you're trying to build surrogates of, to incorporate that into the mathematical structure of the neural network itself. It really, really helps when you do that. And for our case, I think I have, do I have an extra slide on that? Yeah, so in our case, well, we do. So for example, in our turbulence model, you can see that what one of the things that characterizes the turbulence is that you have what's called critical thresholds. So this is a temperature gradient on the x-axis, and this is turbulent heat flux for ion heat flux and electron heat flux. And it's very low. And then at some point, when you go beyond a threshold and gradient, you have destabilization of modes, and the turbulence just shoots up really fast. So it's really important that that you capture both this discontinuity very well, this critical threshold behavior, and also that your different transport channels, electron heat, ion heat, particles, they all actually start from exactly the same place. And also that when you're stable, that you don't have any pop back of flux that's sort of non-physical. And so all the information we actually do try to incorporate into the neural network structure and the training techniques. So yes. Yeah, so does the feedback from the neural network loop back into the reduced model for further improvement? Yeah, that's really another excellent question. So the answer is yes, because I wouldn't say from the neural network itself, but what it does allow is, let's say that the neural network is a very accurate surrogate of the reduced model, then you can use it in tokamak simulation. And now, because it's so fast, you can actually then do validation against hundreds or thousands of different experiments in the same time that maybe in the past you could do 10 or 20. And so suddenly you see in your whole landscape, where are you getting more or less agreement with your reuse model? And then that can most definitely feed back into the physics side. Okay, why does it not agree here? What's characterizing that parameter space? You begin to also look then with higher fidelity nonlinear simulations, and you begin that whole process of model improvement. Yeah, and I see there's a question at the top that I missed. Would you use these neural networks to still understand what's going on in the plasma physics-wise? So I think the answer is, well, so first of all, by these neural networks, I assume we're discussing these surrogate of the turbulent case, so that example. So then the answer is still is partially, I would say, because you get so let's say you get some optimized regime and you see, okay, wow, great, my temperatures are high. Some of it you can just understand by let's say, how the system, okay, let's put it like this. If the system evolves to that optimized state because of known correlations, that that the, if you increase if you change the magnetic geometry in a certain way, then you get better temperatures. But then what happens in the simulation is things begin to feed back on top of each other. You get positive feedback loop and you get there. So you still learn that physics. It's just what the neural network helps you with is to explore different trajectories to begin to trigger those positive feedback loops. So for that, you still most definitely understand. It could be that in other cases, you don't actually understand why your confinement is good. Like you are reproducing your model, but you can't really look inside then the model to see why is turbulence reduced. But then in that case, you can just go back to the original model and begin to look at the equations and begin to do tests, and then you uncover the physics from there. Because the neural network itself is just a black box, but if it reproduces something else that you have, then you can go back to what you have and explore the physics in there a bit deeper.
I think that's all the questions, right? Yeah, I don't see anything else. Excellent. Thank you for the talk, Jonathan. It's much appreciated. And then we will now move on to our last speaker of today, which is Jean-Paul van Keulen, who's recently written a book, which I talked about a bit in the first presentation. So I'm sure he has much more to say on this and many other interesting avenues of fusion. So without further ado, please take the floor, Jean-Paul van Keulen. Jean-Paul, we're not quite hearing you yet. I'm not sure if you are already talking or not.
Horen jullie mij zo?
Jazeker.
Oké.
Dit is perfect. Ja, ik ben nou goed te horen.
Ik mag het verhaaltje in het Nederlands houden. Dat vind
ik
ik
mag het zeker in het Nederlands houden. Ja, dus ga gerust je gang.
Oké, nou en het gaat, zoals de vorige slide liet zien, over exotische fysica. En wat ik daarmee bedoel, daar kom ik zo op. Wie ben ik? Ik ben geen fusiewetenschapper, dus dit praatje gaat iets minder diep dan de vorige 2, 3. Ik weet niet of dat een voor- of een nadeel is voor jullie op dit punt van het programma. Ik ben wetenschapsjournalist, ik heb sterrenkunde gestudeerd en ik heb eerder gewerkt voor Kijk, de ingenieur en New Scientist. En daarnaast ook gefreelanced voor bladen als Quest en EOS en voor de Volkskrant. Sinds 1 september ben ik fulltime freelancer. En sinds een jaar of 10 rapporteer ik ook over kernfusie in onder andere de bladen die je hier ziet. Daarnaast heb... ga terug. heb ik een aantal boeken geschreven. De eerste 2 deeltjes dierentuin, deeltjes safari gaan op deeltjesfysica. De derde verstoppertje spelen met aliens over hoe je tekenen van buitenaards leven zou kunnen zien. En de laatste en de nieuwste van dit jaar is de fusiedroom. Die kunnen jullie dus gratis aanvragen. Dat zou ik zeker doen. En het punt van het boekje is een beetje, sowieso om kernfusie uit te leggen op een behapbare manier. Dus ook een middelbare scholier zou er zeker wat mee moeten kunnen. Een ander deel van het verhaal is om kernfusie een beetje de goede plek in het debat te geven. Omdat een beetje de uiterste zie je vooral veel van mensen die zeggen, kernfusie is er altijd pas over 50 jaar, oftewel nooit. Ja, dan doe je het werk waar we net zoveel over gehoord hebben wel een beetje tekort, want er wordt wel degelijk vooruitgang geboekt. En ik ben zelf heel benieuwd waar dat toe gaat leiden. En aan de andere kant heb je mensen die denken dat kernfusie het hele energieprobleem binnen afzienbare tijd gaat oplossen. En dat we dus niks met wind of zon meer hoeven zodra dat in zicht komt. En dat is ook weer niet helemaal waar. Dus vandaar onder andere dit boekje. Waar ik het vandaag een beetje over wil hebben is, ITER hebben we nu vooral over gehoord. De grote reactor in Zuid-Frankrijk die nu in aanbouw is. Ik heb net even gecheckt, hij is voor 3/4 af nu. En in 2025, zoals eerder gezegd, moet er dan voor het eerst een plasma in deze reactor gebracht worden. Wat je daar niet altijd bij hoort, dat plasma is gewoon waterstof nog. Dat is niet deuterium en tritium, de brandstof waar het uiteindelijk om moet draaien, waar je daadwerkelijk energie mee kan opwekken. Dat is zo'n 10 jaar later, 2035. Dat is dat punt ook waarop ITER dan 10 keer zoveel energie moet gaan produceren dan dat het erin gaat. Maar dan zijn we er nog lang niet, want ITER gaat geen stroom aan het net leveren. Dat moeten de demo-reactoren laten zien. Ook al genoemd, die ontwerpen daarvoor moeten rond 2030 klaar zijn. De bouw zal begin jaren 2040 gaan starten. 2055 zijn die dan af. En dan zijn we er nog niet. Want dan moet de industrie het gaan overnemen, voordat je echt overal ter wereld waar dat zinnig is, krachtcentrales volgens een van de demorecepten hebt. Nou, voordat dat eens zover is, is het rond 2080. Ik ben dan 102. Het punt is, kernfusie via de ITER-route is een route van de lange adem. En er zijn allerlei partijen die zeggen van dat kunnen wij sneller. Wij kunnen een compactere, goedkopere reactor bouwen. En de claim die je dan bijvoorbeeld hoort is, we hebben binnen 5 jaar een reactor die achter op een vrachtwagen past. Nou, dat is natuurlijk een heel ander verhaal dan ITER en dat klinkt super veelbelovend. En ik wil 2 nu van dat soort reactoren bespreken, want het zijn zeker interessante alternatieven die op vaak hele andere manieren werken. Maar er zit ook een waarschuwing bij, want die bouwde claims waar dat soort bedrijven mee komen, neem die vooral met een korrel zout. Nou, de eerste waar ik het even over wil hebben is eigenlijk mijn favoriet. Ik vind het een heel cool ontwerp. Het hart ervan is een volume, een bol met vloeibaar metaal. Die roteert, waardoor in het midden van die bol metaal een vortex, een soort zo'n kolkje zoals je in een leeglopend bad ziet, ontstaat. En daar kun je plasma inspuiten, deuterium en tritium, net als in ITER. Wat je ziet is dat ding is omringd door allemaal zuigers, een stuk of 300. En het plan is dat die zuigers allemaal tegelijk bats naar binnen toe schieten, elk op een eigen aanbeeldje en zo'n schokgolf creëren naar binnen toe. Die zorgt dat dat plasma fusiereacties gaat voortbrengen. Nou, die verhitten dan dat vloeibare metaal eromheen. Daar haal je energie, daar maak je stoom mee. Die stoom drijft een turbine aan. Dat levert dan elektriciteit op en de energie om die zuigers aan te drijven. Nog een ander slim trucje daarbij is, bij deze reactie komen, zoals eerder ook al vermeld, neutronen vrij. Nou, normaal is dat vervelend, want neutronen die vliegen je reactor uit, kunnen op atoomkernen botsen en die radioactief maken. Hier is het idee dat die neutronen op lithiumkernen in dat vloeibaar metaal botsen, waardoor die gaan vervallen. En als die vervallen, leveren ze tritium op. En dat is een van de ingrediënten van je brandstof. Dus dat moet bij demo uiteindelijk ook de bedoeling zijn. Dit reactorontwerp gaat zelf het moeilijker te verkrijgbare ingrediënt van zijn brandstof produceren, door gebruik te maken van de neutronen die vrijkomen bij die kernreacties. Dit is een heel ander soort concept. Maar bijvoorbeeld Tony Donné, nu de directeur van Eurofusion, een Nederlandse topfusiewetenschapper, die is een aantal jaren geleden gaan kijken. En die met het idee, eigenlijk in opdracht van potentiële geldschieters, van wat vind je daar nou van? En die kwam terug met, we hebben er geen gaten in kunnen schieten. Wil niet zeggen dat het wat gaat opleveren, wel dat het best zou kunnen werken. Er zitten geen duidelijke fouten in dit plan. En ook Marco de Baar, de huidige directeur van Differ, die is er onlangs geweest. Nou, die mocht er niet zoveel van zeggen, want ze laten hier dan zo'n non-disclosure agreement ondertekenen. Maar die merkt aan alles dat hij ook zoiets had van, goed plan. Dat gezegd hebbende, ik heb hier 6 jaar geleden al over geschreven. En toen leek het de claim te zijn van, binnen 5 jaar hebben we wel een prototype. De fase waar we nu zijn is dat we weten waar ze dat prototype gaan bouwen. Dus je zit wel weer, zoals helaas wel vaker bij kernfusie, met dat de werkelijkheid zich niet houdt aan de mooie plannen. Ook is het ontwerp veranderd. Eerst was het een bol met zuigers, nu is het, zoals je ziet, meer een soort ring met zuigers rondom. Dat is uit 2017, meen ik. Dus dat is een beetje waar het altijd wringt van, er bestaat een plan op papier, daar wordt een claim aan gekoppeld van binnen zoveel jaar hebben we iets. En dan blijkt in werkelijkheid dat het allemaal toch niet zo makkelijk zit. Maar goed, wel een ontwerp om in de gaten te houden. Ze gaan het dus ook nu echt in Engeland er eentje bouwen. Een andere, TAE Technologies, stond eerder voor Tri-Alpha Energy. Dat begon met een reactor die ze de rioolpijp noemden, omdat het letterlijk een stuk rioolpijp was. Dat was gewoon een buis met apparatuur erin, die in een soort van proefproto, hele vroege schets van een idee moest zijn. Inmiddels is het een ander verhaal, want dit bedrijf heeft $880 miljoen aan investeerdersgeld opgehaald. Daarmee is het met afstand het rijkste bedrijf dat een fusiereactor wil bouwen. Dat is ook echt van geld van Google, miljardairs en weet ik wat allemaal niet, in Californië. En het idee, nogmaals in heel simpele termen, is je maakt aan beide uiteinden van deze buis een soort rookring van plasma, vergelijkbaar met zo'n rookring die een geoefend pijproker kan maken. En die 2 ringen die gaan naar elkaar toe. In het midden vormen die een roterende rugbybal aan plasma, die met de uitsteeksels in het midden die je ziet, dat zijn bundels neutrale deeltjes die rugbybal nog een beetje in vorm houden. En het idee is natuurlijk dat daar kernfusie in gaat plaatsvinden. En het grote nieuws dit jaar was, waar ook diverse nieuwsmedia enthousiast over gerapporteerd hebben, ze hebben een temperatuur gehaald van 50 miljoen graden. Denk je, oké, het is niet die 150 miljoen graden die we in ITER nodig hebben voor kernfusie, maar het is een eind in de richting. Maar dat is het niet, want deze reactor werkt niet met deuterium en tritium, dat zijn 2 vormen van waterstof. Deze reactor werkt met boor en waterstof. Een boor is het 5e element uit het periodiek systeem met een lading van +5. Waterstof heeft lading van +1 als je puur naar de kernen kijkt, en daar gaat het om. Maar dus die stoten elkaar veel harder af dan wanneer je met alleen maar deuterium en tritium aan de slag gaat. En dus moet die temperatuur ook navenant hoger zijn om ze toch te laten fuseren. En hoger is in dit geval 3 miljard graden ongeveer. Nou, ik hiervoor teken miljard graden. En dan is die 50 miljoen waar ze nu de pers mee halen een schijntje. En dat hebben ze ook voor 30 milliseconden gedaan in plaats van uren of zoiets. Wat uiteindelijk de bedoeling zal zijn. En hun claim is, in 2030 hebben wij een prototype dat stroom aan het net kan leveren. Dus zij verwachten in een jaar of 9 op het punt te zijn waar demo in 2055 is. En dat is natuurlijk nogal wat. Als je ziet wat ze aan temperatuur allemaal hebben te overbruggen. Er komt nog een hele route met potentiële problemen. En eigenlijk hun inschatting is, het gaat gewoon zoals we nu bedacht hebben. Dat komt allemaal goed. Nou, hier zijn dus niet betrokken fusiewetenschappers best wel sceptisch over. Het jammer is dat journalisten die mensen niet altijd vragen. En meestal vooral het PR-praatje van zo'n bedrijf overnemen. Waardoor dus het publiek ook te horen krijgt van, in 2030 hebben we al kernreactoren die met fusie werken. Dus waarom zouden we op ITER gaan wachten? Even kijken, ik zie iets in de chat. Waarom gebruiken ze borium? Nou, een voordeel van boriumfusie is dat het boor plus waterstof geeft je 3 heliumdeeltjes en verder niks. Dat is een vraag uit de chat van Anouk. En die verder niks betekent dus, er komen hier geen neutronen bij vrij. Of in ieder geval heel weinig. En neutronen, zoals ik eerder zei, in principe zijn die vorige ontwerp gebruikte die neutronen slim om tritium te genereren. Maar in principe zijn neutronen een probleem, want die maken je reactorband radioactief. Dus dit is de schoonst mogelijke reactie die het minste gedoe geeft met nucleair afval. En dat maakt het aantrekkelijk. Maar het heeft dus het nadeel dat je een hogere temperatuur nodig hebt om het voor elkaar te krijgen. En dat moeten we gewoon zien. Hoe ik dit deel van het verhaal een beetje voor me zie, is als een soort race met als enige serieuze deelnemer is ITER. En ITER zie ik als een soort van logge vrachtwagen die niet al te hard kan en die met een redelijke kans van slagen naar de finish toe rijdt. En al dit soort bedrijfjes waar ik het net over had, dat zie ik als een soort van experimentele Formule 1 wagentjes met mensen daarnaast die staan op te scheppen hoe geweldig hun autootje wel niet rijdt en dat die vrachtwagen binnen de kortste keer gaat inhalen. Maar pas als ze echt gaan meeracen, ga je zien wat ze waard zijn. En dan kan het best dat sommigen helemaal niet vertrekken of na 100 meter al afslaan of exploderen of wat dan ook. Het is... wat deze bedrijven volgen is de high-risk, high-reward strategie. Het is allemaal wat minder bewezen technologie. Ze weten minder goed wat ze allemaal onderweg nog gaan tegenkomen. Maar als ze hun claims waarmaken, dan heb je veel eerder fusie en misschien ook wel veel praktischere vormen van fusie. Een kleinere reactor die je op meer plekken zou kunnen inzetten. En wat ook al een van de vorige sprekers noemde, het zijn vooral investeerders die er geld in stoppen. Dus je hoeft niet te klagen van, niet van mijn belastingcenten. Dit zijn wel mensen die heel brood in zien en daar dus tot honderden miljoenen in steken. En in principe is dat prima, zou ik zeggen. Laat het ze maar proberen. Laat maar een techmiljardair kijken of die het energieprobleem van de wereld een nieuwe oplossing kan geven. Het jammere is dus dat om die investeerders over de streep te halen, daar komen die juichverhalen vandaan. Daar komen die hele bouwde claims van binnen 5 of 10 jaar hebben we een reactor. Terwijl ze denk ik diep in hun hart zelf ook wel weten van dat zou ons ook verbazen. Dus neem dat een beetje mee als dit soort nieuws voorbij komt. Want het blijft gebeuren binnen 10 jaar. Grote stap gezet, de reactor komt eraan. Het zal wel langer duren en de kans is groot dat het niks oplevert, maar het zou kunnen en dat zou heel mooi zijn. Nou kijk ik even op de klok. Ik heb geloof ik in reguliere tijd nog 5 minuten, dus ik wil nog wel eventjes iets over koude kernfusie zeggen. Het is een beetje hoe zeg je dat? Een zwarte paard of zo. Hoe dat begon, in 1989 maakten 2 scheikundigen van de Universiteit van Utah, Stanley Pons en Martin Fleischmann, bekend dat ze een schone energiebron voor de wereld hadden ontdekt, de kernfusie, maar dan dus niet door de temperatuur op een slimme manier heel hoog te krijgen naar die 150 miljoen graden of iets dergelijks, maar gewoon door een proefje basically bij kamertemperatuur te doen. Nou, dat proefje dat zat in elkaar zoals je op het plaatje ziet. Er was een bak met zwaar water, dus watermoleculen waar de waterstof is vervangen door deuterium. In die bak zitten 2 elektronen, er werd een stroom doorheen gejaagd, dat trekt die zware watermoleculen uit elkaar. Die positief geladen deuteriumkernen die trekken dan naar de negatieve elektrode, die was van palladium. En dat palladium maakte, samen met dat deuterium, kwam warmte bij vrij. En dat was meer warmte dan je op scheikundige wijze zou kunnen verklaren. Dus was de conclusie kernfusie, koude kernfusie. Kernfusie zonder ingewikkelde tokamaks. Nou, dat nieuws sloeg toen als een bom. Het strookte niet met hoe men in de reguliere fusiewereld tegen fusie aankeek, maar het was zo veelbelovend dat overal, ook in Nederland, Nieuwegein destijds, meen ik, dat proefje herhaald werd om te kijken van, is dat zo? Is het zo makkelijk? Hoef je alleen maar een bak zwaar water te nemen en een batterij, bij wijze van spreken, en palladium? Daar leek hier en daar wel iets uit te komen, maar uiteindelijk was toch op de meeste plekken de conclusie van, nee, het werkt toch niet. En ondertussen waren ze in Amerika ook een beetje aan het rotzooien, want bij kernfusie komt gammastraling vrij. Nou, dat leek hier bij Pons en Fleischmann ook het geval te zijn, maar er was een plaatje van, er stond dat piekje van die gammastraling op de verkeerde plek en alle andere piekjes die je dan ook zou verwachten, die stonden helemaal niet op dat plotje. En toen werden ze erop gewezen en toen verplaatsten ze gewoon het piekje naar waar het wel had moeten staan. En zo waren er meer van die dingetjes, waardoor ook het vertrouwen in hun als wetenschappers heel snel erodeerde. Waardoor eigenlijk al gauw de conclusie was van het was ook te mooi om waar te zijn, laat maar. Pons en Fleischmann die zijn naar Frankrijk gegaan, die zijn wel eigenwijs doorgegaan met dit soort proefjes. Ook elders in de wereld zijn er kleine clustertjes en eenlingen die hierop doorgegaan zijn. Nou, ik heb daar in mijn eerste artikelen over fusie altijd misschien wat al te makkelijk lacherig over gedaan. En dan krijg je boze brieven. En dacht ik op een gegeven moment van, laat ik daar toch eens even wat serieuzer naar kijken. Toen heb ik zo'n koude fusiewetenschapper die een beetje respectabel is, gemaild van, wat zijn nou de 3 beste artikelen die je hebt? De meest overtuigende 3 verhalen. En met die verhalen ben ik naar hete fusiewetenschappers heen gestapt en gezegd van, jongens, ik weet hoe jullie hierover denken, maar kijk nou eens sec naar deze 3 artikelen. En zeg me of wat mankeert eraan, of zit er misschien toch wat in. Laten we nou gewoon eens even puur naar die 3 goede papers kijken. En dan negeren we al die andere. Nou, hebben ze gedaan. Dat was heel netjes van ze. En waar ze mee kwamen was eigenlijk van, we kunnen deze omschreven proefjes, want die orde van grootte is het wel vaak, helemaal niet nadoen. Er staat wel, we strooiden palladiumpoeder in het water, maar niet hoeveel. Was het 20 gram, was het 50 kilo, staat er niet. Of ze vermelden wel de stroomsterkte, maar niet hoeveel volt of zo. Dus ze zeiden even, je kunt dit niet nadoen. Het klopt ook niet met elkaar. Het ene experiment spreekt het andere tegen. Dus het is helemaal niet alsof ze samen één goed beeld van de werkelijkheid onderschrijven. Je moet ze allemaal los zien en ze refereren ook nauwelijks naar elkaar. Dus het zijn echt eilandjes die allemaal hun eigen ding doen en het ook nog rete slordig opschrijven. Ik dacht van oké, dat is dan de mening van de hete fusiewetenschappers, maar die hebben ook hun belang. Dus laat ik het nogmaals even aan nog een koude fusiewetenschapper vragen van wat vind je van dit oordeel? Natuurlijk wel iemand die een beetje boven de partijen staat en die zei tot mijn verbazing, dat zal ongetwijfeld kloppen. Ik hoef niet eens te weten welke 3 artikelen het waren. Ze zijn allemaal zo slecht, bijna zonder uitzondering. En dat was dus iemand die wel gelooft dat dit effect bestaat, maar die meteen onderkent van die artikelen daarover die zijn gewoon eigenlijk, daar kunnen andere wetenschappers niks mee. En hij zelf, zij bekende moet ik in dit geval wel zeggen, zei van ik kom hier normaal nog niet voor uit, maar ik moet het toch maar een keer zeggen, hij gelooft ook zelf niet meer dat er sprake is van fusie. Hij denkt wel dat er iets gebeurt in dat palladium of waar je dan ook mee werkt, maar volgens hem zit de oplossing in vaste stoffysica. En is de tragedie wat hem betreft dat vaste stoffysici zich niet met dit probleem bezighouden. En het vakgebied is ook een beetje besmet. Dus reguliere instituten en labs doen er weinig mee. En de durfkapitalisten die wel geïnteresseerd zijn, die willen een energiebron. Die willen een kernfusiereactor die op wonderlijke wijze bij kamertemperatuur werkt. Dus die gaan niet een vaste stofvakgroep geld geven om te onderzoeken wat voor ander effect je hier misschien zou kunnen spelen. Nee, die geven hun geld, als ze het al ergens aan geven, aan iemand die zegt, ik bouw er een reactor van voor je. En dat is dus denk ik voor mij nu mijn kijk op het koude fusieverhaal. Het kan best dat er iets gebeurt, dat het met fusie te maken heeft, dat is heel erg onzeker, dat je er binnen afzienbare tijd een reactor op kunt baseren ook. Wil niet zeggen dat er niks gebeurt. Ik zou niet willen beweren dat al die mensen die warmte meten met hun proefopstelling, dat die liegen of dingen zien die er niet zijn. Maar meer nog dan bij die reactoren die ik net besprak, hele grote korrels uit. Oké, dat is een beetje mijn verhaal. Ik zie dat er nog wat dingetjes in de chat staan. Kijk of ik daar nog... Ja, Anouk, vrouwen zegt, klopt, op diff is er toen een paar nachten doorgehaald, het werkte niet. En inderdaad, ja, Oké, zijn er verder nog vragen die ik op dit moment kan tackelen? We zijn nog redelijk binnen de tijd gebleven, zie ik.